Welcome to the Characteristics and Graphs of Logarithmic Functions podcast. This is for students that were absent on Friday. All right, so first we're going to look at some key features of our logarithmic functions. All right, so our x-intercept is 1. There's no y-intercept. The x-axis is a vertical asymptote. If your base is between 0 and 1, your function is decreasing. So on the left, we have an example of a graph that is decreasing, a logarithmic function that's decreasing, because the base is between 0 and 1. And if b is greater than 1, our function is going to be increasing. So on the right-hand side, we have an example of logarithmic growth. Okay? The graph is smooth and continuous. It has no sharp corners or edges. And it is always either decreasing if it has the base between 0 and 1, or it is always increasing if its base is greater than 1. Notice the domain and range, they are switched from the exponential functions. Our domain is 0 to infinity. We're not going to cross that x-axis. And our range, we're not going to cross the y-axis. Our range is negative infinity to infinity. All right, so logarithms are nothing more than exponents. We can use the fact that a logarithmic equation is just the inverse of an exponential equation. So we're graphing logarithmic equations, and this is in your notes. We want to rewrite logarithmic equations as an exponential function. We want to evaluate the exponential function where y is the exponent and x is the result. That's switched from our exponential functions. We're going to graph the points and connect to graph our base graph. And don't forget your vertical asymptote, and then translate the function if our function has been transformed in some way. In other words, we have something added to our whole function or something added to x. So first we're going to look at graphing 2 to the x and g of x equals log base 2 of x in the same plane. So here are our coordinates. Notice that our x coordinates for the exponential are the exponents, and the y coordinates are the result. For the logarithmic, the x coordinates are the result, and the y coordinates are the exponent. Okay? So when we write it, our base, we're going to raise it to the y power, and it's going to equal x. This one's in your notes, so let's graph these two. All right, let's graph the exponential function first. I'm going to put a coordinate little table right there. So this is for y equals 2 to the x. So I'm going to raise 2 to the negative 2, negative 1, 0, 1, 2, and 3 power. So 2 to the negative 2 is 1/4. 2 to the negative 1 is 1/2. 2 to the 0 is 1. 2 to the first is 2. 2 squared is 4. And 2 cubed is 8. All right? Remember, this function has a horizontal asymptote at y equals 0. And so let's graph our points. All right, so we have the point negative 2, 1/4, negative 1, 1/2, 0, 1, 1, 2, 2, 4, and 1, 2, 3, 4, 5, 6, 7, 8. So 3, 8. And this graph is not going to cross, well, you know, it looked a little nicer, I have to say, earlier today. Maybe the board is tired because I put the little glitch in there. So I didn't really have the glitch earlier today. So anyway, here's our graph of, let me see if I can fix that. Y equals 2 to the x. How does that look? Other than the fact that it looks like it wants to bop back up again. Oops. It doesn't look too bad. There we go. I'll take it. All right, so now let's graph our other graph, our y equals log base 2 of x. So in this case, there is our function already written in exponential form. So 2 to the y equals x, because the y is the exponent, the 2 is the base, and this is the result when you raise to a power. All right, so into my y's, I'm going to plug in my exponent. So that's where I'm going to have negative 2, negative 1, 0, 1, 2, and 3. And then 2 to the negative 2 power, and my x will be 1/4. 2 to the negative 1 will be 1/2. 2 to the 0 will be 1. 2 to the first will be 2. 2 squared will be 4. 2 cubed will be 8. All right, so now we're going to be graphing the points 1/4, 1/4, -2, 1/2, -1, and so forth. So notice the x's and y's are switched. This graph has a vertical asymptote. And let's graph our points. So 1/4, -2, 1/2, -1. Actually, I'm going to graph that in black so it doesn't blend into that asymptote there. And 1, 0, 2, 1, 4, 2, 5, 6, 7, 8, 3. So here is our logarithmic graph. Oops, oh, I just missed that point. There we go. All right, so the blue graph is y equals 2 to the x, and the black graph is y equals log base 2 of x. All right? So now you can see them together. On this one is in your notes. On this one, I just wanted to have the function and its inverse together so that you could see the reflections over the line, y equals x. They're horizontal and vertical. One graph, the exponential has the horizontal asymptote. The logarithmic has the vertical asymptote at x equals 0. For the logarithmic, the domain is 0 to infinity, no negative numbers. But our range, because that's the exponent, is -infinity to infinity. All right, so just for this one graph, we graphed them both. Normally, we're just going to graph the logarithmic. Okay? So let's look at just graphing the logarithmic graph. We're going to graph y equals log x. And when we rewrite it, this was y is the exponent. If there's no base written, it's understood to be 10, so our base is 10, and the x is the result. So when we rewrite that in exponential form, it will be x equals 10 to the y. So we're going to plug our exponents in for y, and I'm only going to use -1, 0, and 1. 10 to the -1 is 1/10. 10 to the 0 is 1. 10 to the first is 10. So let's graph those, and let's graph our vertical asymptote. We have a vertical asymptote here at, there we go, x equals 0. So we have the point 1/10, -1, 1, 0, and 2, 3, 4, 5, 6, 7, 8, 9, 10, 1. The next point, if we wanted to have integer values just, would be at, ooh, I really overshot my point there. Our next point would be at 102. So that would be quite a ways away. I guess that looks okay. So obviously we're not going to be graphing that point. I don't have enough space. It'd be off the board. The logarithmic functions are one of the slowest growing graphs. They are growing, it's just very, very slowly. So our domain is 0 to infinity. Our range is -infinity to infinity. Okay, let's graph another one. All right, so now we have a decay. Our base is between 0 and 1, and this one's in your notes. We have y equals log 1/3 to the x. All right, so we rewrite that in exponential form. Base raised to a power gives us the result. All right, so we'll plug in this one. Let's plug in 2, 1, 0, -1, -2. And if I raise 1/3 to the second power, it would be 1/9. 1/3 to the first power is 1/3. 1/3 to the 0 power is 1. I probably should have moved my y values down. 1/3 to the -1 power is 3, and 1/3 to the -2 power is 9. I guess in the end they're sort of spaced together. All right, so we'll graph our vertical asymptote. We have a vertical asymptote right there at x equals 0. All right, so now we're going to be coming from above and going down because this is decay. So we have the point 1/3, 2, and then, excuse me, 1/9, 2, 1/3, 1. So that should be just a little further out, I guess. This one should be a little further in. 1, 0, and then 3, 1, and then 4, 5, 6, 7, 8, 9, 2. All right, so now our graph is coming from above. It's decreasing. And there we go. All right, our domain, 0 to infinity, all positives, and our range, -infinity to infinity, all values, because that's an exponent. And anything can be an exponent. Okay? So I hope you see that these are really no more difficult than graphing an exponential. It's just that we're going to have to rewrite it into exponential form. All right, so graphing exponential functions in logs. All right, here's two examples. We have y equals 3 to the x and y equals log base 3 to the x. All right, notice that, again, the x and y values are switched. So for the exponentials, which is on the left, the x values are exponents, the y's are results. For the logs, on the right, the x values are the result and the y values are exponents. And you can see that these are going to be reflections of each other over the line y equals x. So this line back here, where we had that diagonal line, was not because there's a slant asymptote. There's not. It's just to show you that those two functions are reflections of each other over that line. Right? Let's graph another one. I think I have one more maybe. Oh, no, I have the whiteboard practice. So we skipped the whiteboard practice for you. And actually, the next thing I have is these are in your notes. I just wanted to go over the transformations. All right, so we have our vertical shifts. And it's the same as our other functions. If you add or subtract something to the whole function at the end or the beginning, so y equals log x plus 3 is the same as y equals 3 plus log x. And y equals -4 plus log x is the same as y equals log x minus 4. It shifts it up and down. It doesn't change the domain, or range for that matter, and it doesn't change your vertical asymptote. It just shifts the function up and down. So here, all I have to do is take the points on my base function, y equals log of x, and shift them up 3 to graph y equals log of x plus 3. Or shift them down 4 to graph y equals log of x minus 4. Okay? So I did put this in your notes. I also put the horizontal transformations. So horizontal shifts, same as other functions, move it right and left. It has to be hooked onto the x value. So in other words, it's going to be inside the parentheses. So if we add to x, it's positive. We're going to move left, just like every other function we've seen. If we subtract from x, it's going to move right. Right? And our vertical asymptote and domain will change on these. So the blue graph in the middle there is y equals log of x. Its domain is 0 to infinity, and it has a vertical asymptote of x equals 0. The next graph, the green graph, is y equals log x plus 2, with the x plus 2 in parentheses. Right? So positive 2 means that it's going to shift it 2 to the left. So all we have to do is take our base graph and move all the points 2 to the left. We have a new vertical asymptote, x equals -2, and our domain will be -2 to infinity. The red graph on the right is y equals log x minus 4. We see an x minus, which means it's going to move to the right, and it's going to move 4 to the right. So all we have to do is take the points on our base graph and move them 4 to the right. We have a vertical asymptote at x equals 4. Our domain is going to be 4 to infinity. Okay? So just, very similar, quite honestly, to our exponentials. It just flipped. All right, here we have reflections. All right, so we have two types of reflections for a logarithmic function. These maybe look a little bit different. I don't think the first one does, where the negative's in front. So if the negative's in front, that's going to make our y values negative. Right? And so we're going to be reflected over the x-axis. Right? So if it's in front, y's are negative, it's reflecting over the x-axis. If the negative is on the x, we're going to reflect about the y-axis. In other words, since my x values have to be positive, and I've got a negative on my x, I'm going to only plug in negative values. That won't change our vertical asymptote, but that will change the domain to -infinity to 0. Okay? And this is the last thing we're going to go over because it's the last thing we went over in class, and that's vertical stretching and shrinking. And this is different than exponentials. They did not have this vertical stretching and shrinking. So when we have a number greater than 1 in front of our graph, it will stretch the graph vertically. If we have a number between 0 and 1, it will shrink our graph vertically. Now, how we calculate this out is a little bit different. Now, using the power rule, remember that a log is an exponent and a coefficient is an exponent because we can move exponents in front. All right? We can move them in front or we can move them back as an exponent. And that's our power rule. Because logs are exponents, and what do we do with exponents? We multiply them. So that's why the 5 can move in front, because we would multiply it. So the y values are exponents. We're going to multiply exponents to raise power to power. So that means that we're going to take we're going to keep our x values the same, but we're going to take our y values, and they're going to be 5 times as much in the case of y equals 5 log to the x. So instead, this is the graph of y equals log x. So that means our first point's really not on the graph in terms of an integer, but 10 to the first, so we have a point 10 on the x and 1 on the y, right? Because 10 to the first would be 10. And our base is 10 because it's not written. So on for the red graph, the y equals 5 log of x, instead of having a point 10, 1, we'd have a point 10, 5. Our y values would be 5 times as much. And for the green graph, because we have a 1/5 in front, we would keep all of our x values, but our y values are going to be half as much. So instead of having the point 10, 1, we'd have the point 10, 1/5. Okay? So we'll go over the rest in class, and we'll also do the whiteboard practice. This was, by the way, what's my name in blue? The last closing. So if you still have your notes, go ahead and do the the bell work. Go ahead and do the closing. It was write 3 facts about the graphs of logarithms. And since you were absent and you watched this podcast and you saw me write that on the board, if you have this done on your closing, you'll get an extra point. If you already turned in your closing and you put it on a piece of paper, you're still going to get that extra point. All right, so I hope you enjoyed this podcast, and I hope you learned a little bit about the graphs of logarithms. Bye!